So right now it is April 17th on 1:45 a.m. at 1:45 a.m. And I'm about to go to sleep because I have to wake up at like 7 tomorrow, today morning. So I got 5 hours of slumber. Anyways, today right now I will be doing the first half of the chemistry rap video. Not even the first half, just the first third, because again, I want to go to bed. So I've talked about physics. Now I'm gonna talk about chemistry. Book one. Here we go. I've, Again, I've done this before, but now I'm redoing it because I feel like now I'm more familiar with, what I'm talking about. Chemistry. So chemistry is a bit of it's a bit of a developing subject. You can't really break chemistry down to like you can break physics down to electricity, magnetism, mechanics, optics. You can't really do that for chemistry. You just can't. So right here, I'm gonna skip a few things that I personally find useless, like part one, planet Earth. But I'm still gonna talk about it because people deserve to know, I guess. Like this is really dumb. Observations. Seeing with eyes, feeling with hands, smelling with nose, hearing with ears. But don't be mistaken, because chemistry is probably the toughest. No, actually, biology is the toughest out of physics, chemistry, and biology, but chemistry is the most annoying and the most confusing as well. No, confusing is actually physics. This is annoying. Anyways, we have moved over to chapter 2, the atmosphere. And for chapter 2, again, there isn't much to talk about other than we got the seawater, we got air. In air, we have nitrogen and oxygen. In the sea, we have water and salt. And there are different ways to, fractional distillation of air, and you can fractional distillate many other things as well, like fossil fuels and all that good stuff. You can test for hydrogen. You put a burning splint in some hydrogen. Boop, it's gonna pop because hydrogen is explosive. It's explosive. It's not flammable. It's explosive. So that is why you don't make hydrogen balloons. If you do, you're dumb. You make helium balloons. Hydrogen balloons, imagine that. You can also test for oxygen by placing a glowing splint in front of the oxygen, and the glowing splint is going to relight because oxygen fuels fire. So this is how you're gonna do it. Not much else. There are different ways of extracting water, different ways of extracting salt as well. You can extract water by distillation. You can extract salt by filtration, evaporation, and crystallization. And that's pretty much it. And I have accidentally skipped chapter 3, which is about the ocean. Chapter 4 is about rocks and minerals. It has a bunch of ores. And I don't want to talk about those because those are not important, okay? Okay, what's important is carbon dioxide plus water equals to carbonic acid. And if you heat calcium carbonate, it's gonna break apart and become calcium oxide and carbon dioxide. Now you add calcium oxide into water, okay? And then you filtrate it. It becomes calcium hydroxide or slaked lime. You dissolve it in a solution, it becomes lime water. And if you pass carbon dioxide into lime water, it becomes calcium carbonate plus water. But if it's in excess, it becomes calcium hydrogen carbonate. So it redissolves. Again, the white precipitate becomes redissolved. So this is quite important, even though it's a really basic concept. I mean, the whole book is really basic. Come on. Yeah, that's pretty much it. Chapter 4 is done. Again, it may seem easy now, but oh, you will be so wrong. It escalates. So essentially right now we are talking about the atomic structure. And for the atomic structure, you know the drill. If you've been to, like 7th or 8th or 9th grade, you know that, in an atom, there are a bunch of protons and neutrons in similar numbers in the center of an element. Well, most likely in the same number, but sometimes it's not like that, And then we have electrons sort of orbiting it, and elements, small elements like helium, lithium, beryllium, boron have like a small number of electrons orbiting it. But if you're talking about, uranium, neptunium, then you got lots of like shells of electrons just surrounding it. And that's why those elements are radioactive, because they can decay anytime. They have too many electrons. Just lose a couple of electrons, lose maybe 2 protons and 2 neutrons, and hey, you just alpha decayed and beta decayed left and right. And that is why elements can be radioactive, especially for large elements. But there's that. Yeah, not much to talk about here. Not much. Okay, we got isotopes. And of course, isotopes are basically elements where the number of neutrons are actually more than the number of protons. It's an ion if the number of electrons are different than the number of protons. The number of protons is basically the atomic number. And if there are fewer electrons, it's a negative ion. If there are fewer electrons, it's a positive ion. It's a cation. And if it's more electrons than protons, then it is a negative ion, aka an anion, not an anion. Okay, so we got the periodic table. Easy peasy. One thing about the periodic table is that I fucking hate periodic tables that don't show me their mass numbers. Mass numbers are so important. Okay, if you don't show me your mass number, I'm gonna kill you. Okay, I'm gonna kill you. Also, this is not very accurate, so I wrote down the updated names for ununtrium 113. Now it's moscovium, apparently. Ununpentium 115. It's now nihonium, japanium. We got tennessine and oganesson. Man, who are naming these elements? Nihonium? Did a Japanese guy find this out and named it after the country? I don't know. Anyways, periodic table. What you need to know is all the elements right here. Group 1, they're called alkali. Alkalis. Yeah. Or alkali metals. And right here they are alkaline earth metals. And then we jump over to group 7. These are called the halogens. Fluorine, chlorine, bromine, iodine. And for groups 1 and 2, as you go down, it becomes more and more reactive. But for halogens, as you go down, it becomes less and less reactive. And we got the noble gas, group 0. The helium, the neon, the argon, the krypton, the xenon, the radon, the oganesson. They are very unreactive because they are noble gases, because they already have 8 electrons on their outermost shells. They don't need to gain one or lose one. They're totally fine. They don't need to do any shenanigans to, in order to be unstable, in order to stabilize themselves anyways. So, they're chill. All right. That's pretty much all you need to know. Okay, now for bonds. There are a few bonds. First of all, we get the ionic bonds, and here are some examples, some common cations. There's the +1 cation, +2 cation, +3. We got the anions here as well. And you pretty much have to memorize those. The hypochlorite ions are you need to memorize them. Like back in 10th grade, we would have like daily quizzes, just quizzing us if this is an anion or a cation and what is its charge and all that good stuff. Permanganate, manganate, chromate, dichromate. We really need to memorize that stuff. So ionic bond is basically when an element basically giving an electron while the other receiving one, or 2, or 3, doesn't matter. But usually it's formed between a metal and a non-metal or semi-metal. And you know how to name them, just the cation and the anion, like sodium, cation, chloride, anion, easy peasy. Magnesium, hydroxide, iron, oxide, calcium, carbonate. It's really easy. So I'm not going to dwell on that too much. Metallic bonds, basically for metallic elements like aluminium or tin. Each element basically give off 2 electrons, but not to a specific element, but to a sea of electrons that don't particularly have a leader nuclei, So, they're just floating around in the sea and they're all sharing these electrons. That's why they're all stable. The electron sea, the delocalized electrons, that's why they are conductive. That's why metals are conductive. All right, now we have the good old covalent bonds. Instead of giving and receiving electrons, they share electrons, and this only happens for non-metals, between non-metals or between semi-metals, or non-metals and semi-metals, like this one where they're all just sharing it. Really basic knowledge, really easy. And then we got the formula mass, the drill. I've talked about it. Basically like carbon is 12. It's the 6th element, but everybody knows it's friggin' 12. Carbon 12, no questioning. Oxygen 16, no questioning. Hydrogen 1, nitrogen 14. Boom. I think sodium is 23.1 and sulfur is 32.1. Wow. Sodium is 23.0. See, this is why the periodic table needs mass numbers. All right. Now we have structures. This is important. Structures. We have 4 kinds of structures. As you can see right here, we have 4 kinds of structures. We have the simple molecular structures. We have the giant covalent, giant ionic, and giant metallic. For giant metallic structures, they're basically a giant piece of metal. For giant ionic structures, it can be many different ionic compounds. There's only 3 kinds of giant covalent structures. 2 of them are carbon. One of them is silicon dioxide, or just silicon structure. Or it can be a diamond, just a bunch of carbon together forming a bunch of tetrahedrons. or it can be carbons in layers, aka graphite. You know, a lot of people mistake, like, oh, if you want to turn graphite or coal into diamond, just crush it. But actually, you need to heat it up as well and make it really hot so that, you know, more bonds can form. Like, you can't just crush it and expect something shiny to come out of your hand. Like, are you dumb? Anyways, simple molecular structures here. You know, there's a whole table I've made in my notebook about, you know, the properties and features of each kinds of molecular structures. You guys should check it out. It's a bit of a mess, I know. But yeah, again, you need to memorize this. I thought there's a roach. First of all, strong bonds, covalent bond is the strongest. There's no doubt in that, you know. Melting point, the highest one, covalent, of course. The hardest one is giant ionic, actually. The most soluble one is ionic as well. Covalent is not soluble at all. And most conductive is a simple molecular structure or giant metallic structure. If the giant ionic structures are molten, they are conductive. And graphite is actually conductive because they have, I think, mobile electrons as well in between layers. Yep. And hey, look, we have a bit of a tesseract going on with cesium chloride, which is somewhat special. Other than that, okay, now we have the metal reactivity series. I have memorized the whole thing in Cantonese, not the entire series, but the most common elements. I just memorized it, all 14 of it. So it's potassium, sodium, calcium, magnesium, aluminium, from the most reactive to least, and then these 5 you extracted by electrolysis, and then zinc, iron, tin, lead, copper, and then it's mercury, silver, platinum, gold. For the next 5, you do it. You extract them by carbon reduction. Basically, heat them up with carbon monoxide or carbon dioxide. Actually, carbon monoxide or just carbon. Carbon dioxide doesn't really work. And then for the next 2, the mercury and silver, you extract them by heating. For gold and platinum, you just dig them. You don't even need to heat those ores. You dig it out, and then you're cool. That's why Minecraft is not that accurate. Like, yes, you need to burn iron ore with coal, but you don't actually need coal to extract like a silver ore. I mean, you need coal for the heat, but if you have the heat, it's already good enough, and you don't even need to smelt gold ore theoretically, unless the whole thing is, I don't know. That's it. Book 1. I feel like I should be reading off of my notebook here, because it's going to get very confusing, and my notebook is somehow even better than this, which is weird. Oh yes, I forgot to mention, this is the reactivity series and how see this is a mess. Okay, so water can react with all the elements here, from here to here, as you can see. But for the first 3 elements, it becomes hydroxides, and then these becomes oxides. Acids can react from here to here. It cannot react with copper unless concentrated sulfuric acid for other reasons. And the flame can react until mercury. All right. Boy, oh boy, am I tired. So, acid plus metal equals to salt plus hydrogen. A salt doesn't have to be table salt, which is sodium chloride, because sodium chloride is not harmful unless, in the event that sodium chloride is harmful, that is when somehow there is that is when somehow we consume potassium, and the potassium displaces the sodium in sodium chloride, and then at the same time something else, say a fluoride, displaces the chloride, and then there's chlorine gas in our bodies, which is toxic, and at the same time there's sodium, which blows up when it touches water. So in that case, then we shouldn't consume table salt, I guess. It's hypothetical. Maybe I'm wrong. I don't know. But like, in the event that sodium ion becomes reduced, which is incredibly difficult, and for some reason the chloride ions get oxidized for some reason, which is really tough. Like it's not an easy feat to oxidize chloride ions, okay? It's not an easy feat. You can do it by consuming fluorine, but then again, why would you do that? It's just as toxic as chlorine, if not more. Anyways, acid plus metal hydroxide or plus metal oxide also equals to salt plus water. If it equals to carbonate of sorts, it becomes carbon dioxide plus salt plus water. Simple rules, really basic. Everybody knows it. Okay, as some acids ionize, like HCl, hydrochloric acid, or a sulfuric acid, H2SO4, or HNO3, nitric acid, H2SO4, of course, 2 dibasic, HCl is monobasic because only one H, and H3PO4 phosphoric acid has it's tribasic because in one molecule there are 3 hydrogen atoms that can be ionized. So it makes it 3 times more concentrated if the same number of moles of that molecule. If you know what I mean. Again, chemistry is pretty abstract, We're down to the particle shit, But we got alkalis as well. We got sodium hydroxide, the classic, and we also got the ammonium, also a classic. Except ammonium is really weak. Ammonium doesn't ionize in water all that well. Yeah, okay, now this is incredibly important. In excess sodium hydroxide, only 3 types of metal ions will react to form a solid, of course, and then redissolve. And these 3 metal ions are aluminum, lead, zinc. And there are specific formulas for it. If you know what's going on, formulas, one compound plus another compound equals to a product. You got to learn the basics. And same goes for excess ammonia. And these 3 metals are silver, copper, zinc. I memorized it, I know. What you also need to know is that when nitric acid decomposes, it releases nitrogen dioxide, which is brown. And again, you need to memorize that. And concentrated sulfuric acid is oxidizing and dehydrating. The reason why it's oxidizing is that it can be reduced very easily. But then again, you need to memorize that shit. Concentration. Okay, so again, this can be quite confusing. So I don't even know how am I gonna explain this. Mass. Okay, it's 215 now. Mass in the unit of grams over its molar mass, which is a gram per mole. Also, the mass numbers you see in the periodic table, they become the number of moles. Number of moles does not equals to the number of molecules. Number of moles times 6.022 times 10 to the power of 23 is the number of molecules. That is the Avogadro's number. Now you have the number of moles. Number of moles per dm cube, or big M, equals to the molarity of the solution, which is the concentration. And we also got the concentration of the solution, which is dumb because you shouldn't call this concentration. You should call this something else. Like, well, technically it is concentration, gram per dm cube, but is it really molecularly concentration? Not really. It's just the, basic mass concentration, which is basic, which is dumb. So yeah. Dilution is a thing as well. MV equals to MV again. So number of moles. Molarity times volume in dm cube, which is basically 1000 cm cube, equals to number of moles. So when you dilute something or dilute something, the number of moles remain. Volume changes, molarity changes, of course. But yeah, there's that. It took me a while to understand this. All right, there's the different types of indicators. We got the universal indicator. We got the phenolphthalein, which is better to test for strong alkalis. We got the methyl orange, which is better for testing strong acids, and we got the litmus, which is more useful both ways. All these are pretty useful in titrations, which I will talk about later. Titration is one of the biggest things in chemistry. Basically, you put a conical flask here, you put a barrette here, you hang the barrette with a stand-in clamp, and you put something known in the barrette, like something with known volume, known molarity. So you put whatever is in here, say an alkali here, so you titrate it against acid, or something acidic here, and you titrate it against alkali. And you see how much of this is taken to neutralize this, to turn this acid or alkali to something neutral. And so with this method, you can actually figure out how concentrated is this. This is called the titration, which is incredibly important. And there's also the whole thing with strong acids versus weak acids. Weak acids like ethanoic acid, aka vinegar, which only dissociates very, very slightly. Okay, here we go, titration. And of course you need an indicator to know when your sample is being neutralized. Other than that, there's not much going on. There's the whole thing where it teaches us how to prepare salt. One thing to keep in mind is you don't want an irreversible reaction. Say you're trying to convert between some chloride and some nitrate, like it doesn't work that well. But there are exceptions, of course, like barium chloride. It's not soluble, right? But that's an exception. All right, one last thing before I go. Fossil fuels. Now, what you see here is the fractionating column. You pass fossil fuels into this fractionating column, and it sort of splits up. We have the refinery gas, petrol, naphtha, kerosene, diesel oil, fuel oil, lubricating oils and waxes, and bitumen, in the order of decreasing boiling points. Actually increasing. That's what's up. And we have the whole shenanigan with the combustion, CXHY plus, oxygen becomes carbon dioxide and water, and you need to balance it out. Really easy stuff. Really basic stuff as well. So today, despite today, despite being very moody and not being a good day at all, you know what? I'm still going to finish up the chemistry stuff. So we're gonna continue with book 3A. Right now it is, I forgot to report the date. Right now it is actually April 18th, 0000 a.m. in the morning. So that's pretty cool. Midnight exact. Yeah, exact midnight. So anyways, let's start off with chemistry 3A, which is a microscopic world 2, but actually it's about how do I explain this? It's actually about molecular shapes and crystals and everything surrounding it. So gave myself a pretty cool tattoo because I'm a loser. Whew. I am tired. I slept for 4 hours only. So we shall start off with what we call as the shapes of molecules. But before we talk about molecule shapes, we should know what is an octet structure, and that some elements do not obey the octet structure. Say normally for CO2, in order to obey the octet structure, they need to share the electrons in a specific way in order to fulfill the octet structure. And if they can't fulfill the octet structure, the molecule usually wouldn't form. But some elements do not form the octet structure, meaning that they don't have 8 electrons on their outermost shells because they want to easily form other kinds of molecules. For instance, we have beryllium. I'm really tired. Beryllium phosphate, where, as you can see, there are only 4 electrons in the central atom. That is the beryllium atom, which is weird. It should be 8. It should be 8. 8 is the good number. But nope, it's 4, because beryllium says, fuck you all. I'm gonna disobey the octet structure. And, okay, boron can do 6, not 8. And then, phosphorus can do a solid 10. And sulfur can do a friggin' 12. And, so even though it looks weird, it's possible. So ultimately, we narrow them down and categorize them into different shapes and structures. We got the linear shape, we got the linear, the tetrahedron, the trigonal pyramidal, the trigonal bipyramidal, the V shape, the octahedral, and the trigonal planar. And there are ones that are symmetrical, like the trigonal bipyramidal. Because they don't obey the octet structure, they becomes kind of symmetrical, like SF6 again. Tell me that is not symmetrical. Oh my god, damn it. So yeah, so now we have the concept of symmetrical. Oh, I can't really. Alright, so now we have the concept of symmetrical and asymmetrical molecules, and we move over to polarity, which is a really important concept in chemistry. So, polarity. Alright, we still have a lot to go. So, right now we have polarity. Man, is it late. So, what is a polarity? First of all, you need to know that every atom has an electronegativity. So, some atoms are super duper electronegative and some atoms are rather electropositive, so less electronegative. The element with the highest electronegativity is actually fluorine, and the atom with the highest electronegativity, theoretically it's hydrogen, but actually it's francium. Not theoretically it's hydrogen, it's francium, but when you're talking about forming molecules, it's kind of rare to have a francium molecule, and hydrogen is really common. So every bond, most of the bonds in the world are actually polar. You know, CH bond, HO bond especially, because O is also one of the more electronegative atoms. So if the electronegativity between the two atoms are huge, the difference of electronegativity, then their bonds are more polar. And yeah. So FON, these are the big three of the most electronegative atoms of all times. They are so electronegative, in fact, their bonds with hydrogens, hydrogen atoms, the HF, the H2O, the NH3, they're so polar, they form a completely new type of bond, and that is the hydrogen bond. And hydrogen bond is a kind of where is it? Okay, right here. A hydrogen bond is a kind of intermolecular force in that it isn't like, you know, covalent or metallic or ionic, but it's sort of in between molecules. So a bunch of HF is going to form hydrogen bonds with one another. That's why they're really soluble in water, because the HF and the H2O can also form hydrogen bonds, but they're not reacting to one another and breaking the covalent bonds. They are still being themselves, you know, their own molecules, but the hydrogen bonds, they remain. So there you go. That is chapter 25. Now moving over to now chapter 26 is about hydrogen bonds and van der Waals forces as well. If molecules don't have hydrogen bonds, they still have a kind of force that sort of attracts the molecules together. Otherwise, it would be really awkward. You know, just one molecule floating in the air. Like what are you doing? So there's this force called the van der Waals force, and the bigger is the size of the molecule, the stronger is the van der Waals force. Also, the greater the area of contact in between the molecules, the stronger the van der Waals force. Look at this. These two molecules have the same molecular formula, same number of carbon, same number of hydrogen, but this one has stronger van der Waals force because it has greater contact, because it is a straight chain. It's rod shaped. But yeah, again, hydrogen bonds. HCl does not have hydrogen bonds because Cl is not electronegative enough. And then afterwards we have a very strange but easy chapter, which is the wait. Oh, I'm not there yet. Okay, this is a pretty weird chapter though. This chapter is crystal. But this chapter only talks about two kinds of crystals. One of them is ice crystals. And why ice is less dense than water, because it has an open structure, because it has more empty space between the molecules, because each H2O molecule form a tetrahedral shape together, and they sort of all connect to one another instead of being packed. So that's a thing. And then we also learned about C60, Buckminster fullerene, which is shaped like a football, and it's all carbon. And there are some fun properties. It has a really low melting point. It cannot dissolve in polar substances like water, but it's strong and hard, and it's not conductive unless you react it with some potassium or any kind of alkaline metal, I guess, but potassium is definitely the better one. A thing I forgot to mention, that if a substance is superpolar and you put a charged rod beside the substance sort of deflects and defies gravity, because the polar power is stronger than gravity, if that makes sense. Polar power, polar force. But anyways, this 3A, pretty easy, not gonna lie. Now we move over to 3B, which is actually the most difficult part in chemistry, redox. Wow. So again, I'm not going to go through the easy bits. That is why I'm going to spend a lot of time talking about this book, because there are no easy bits. Starting off, we have something very practical. Chemical cells. Of course, in a cell, there's the battery, the EMF or the electromotive force, the positive electrode, negative electrode, the electrolyte, the discharge, all the stuff. But what we need to memorize in this chapter, in chapter 28, is there are 6 kinds of very common batteries. We have 3 kinds of common primary batteries: the zinc carbon, the alkaline manganese, and the silver oxide. Extremely common. I should spend a little more time memorizing these cells. We also have the lithium ion, the nickel metal hydride, and the lead acid accumulator. They are the secondary cells that can be recharged, but primary cells cannot be recharged. That is the fact. And then chapter 8 is over. Chapter 28 is over. Now moving over to chapter 29, where the fun begins. Chemical cells. So it took me a very long time to understand the concept of redox. You cannot tell what kind of reaction is happening in this cell if you haven't studied this at all. But okay. Now, I'm going to try my best to explain it in a very condensed way. The way they're connected here, with an electrolyte and a conductive wire going through, one of these metals, the more reactive one, is going to lose electrons and provide it to this side. So the one that loses electrons is the anode. And anode is oxidation, always. I don't care what kind of cell it is. It can be a chemical cell, it can be an electrolytic cell. It's always oxidation. And then for the cathode, which is connected to a positive terminal in a chemical cell, reduction, always. And sometimes the electrodes are inert, meaning that it's not that the atoms in the electrodes get oxidized or reduced. Sometimes it's the electrolyte itself. So again, it can be quite confusing, I understand, and it needs some training. there's this thing called salt bridge. Okay, now it's starting to get complicated. Every time. So we have this thing called salt bridge, and it basically it does two things. One of them is to balance the ions, and one of them is to balance the charges. All right, please stop dropping stuff everywhere on my legs. That would be nice. Now we have oxidation and reduction. Now this is a really simple oxidation and reduction equation where, as you can see, the magnesium, originally it's 0 because it does not have any charge. And then the magnesium becomes +2. It has a charge, you can't see it. If you can't see it, you're dumb. But because it becomes an ion, not just a metal, so it becomes from 0 to +2, meaning that it has lost electrons. But to be oxidized also means you gained oxygen or lost a hydrogen. Any of that combination. And now we have the oxidation number, which is basically their charge, or say okay, how am I going to show you? This is really tough. Like this is really tough. The oxidation number is basically, say, in H2SO4. All right, in H2SO4, the whole thing is 0. It doesn't have a charge, but O is -2. Just look at the periodic table. It's -2 if it's an ion. So -2 times 4, and then H is a +1, so +1 times 2. So 0 minus -2 times 4 minus 1 plus 2 equals to the oxidation number of sulfur, which is 6. Now, there are several kinds of common oxidizing agents. Yep, oxidizing agents, they oxidize others, so they themselves get reduced. But then we have the common reducing agents, which are the ones that reduce others and get oxidized themselves. I have a, I don't know if it's better, but here you go. Okay, so if it in a chem cell, the electrons go from negative to positive, the anode is negative, and the cathode is positive, and you know, and in an electric in an electrolytic cell, it's inverted. It's reversed. That's about it. And in an electrolytic cell. This table is extremely important because, okay, how do you know that when magnesium and copper oxide react, it's going to become copper and magnesium oxide? How do you know? But if you reverse it, you can't do that. Well, look at this table. Take a good look. Magnesium is dying to be oxidized because it's so unstable. But copper's chill. Copper's more stable. So we have this whole table where it has the strong reducing agents, strong oxidizing agents, and stuff. And as you can see in the bottom, high sulfuric acid is dying to be reduced. You know, we need to really memorize this table. Really important. We have a bunch of other small, you know, stuff, redox examples and stuff. One thing to note is iodine in heptane becomes purple, and bromine in heptane becomes reddish orange. So yeah, you know, just all right. Now redox. Now we put that concept in chemical cells. First of all, we have, of course, we have the inert electrodes and the inert electrolytes. There are different kinds of chem cells. And then we have a zinc carbon cell. In a zinc carbon cell, the positive electrode is most certainly the friggin graphite rod, but graphite is not the one that gets reduced. It's actually the ammonium chloride, which is the electrolyte, but the zinc is the one that gets oxidized. That is why if you use the zinc carbon cell for a long time, the zinc sort of just dissolves. And yeah, and then we have another cell called the hydrogen oxygen fuel cell, which is slightly more confusing. It has a higher advantage though, even though it's more expensive. But at the anode, hydrogen plus 2 hydroxide ions, OH minus, equals to 2 water plus 2 electrons. You can actually split up the ionic equations into the anode equation, what's going on at the anode, the oxidation, and what's going on at the cathode, the reduction, and then you add them both together, but you need to balance them both first. So yeah, balancing redox for equations, you need to know how to do that as well. And then we have electrolysis, which is basically the reverse of chemical cells. I'm not gonna dwell too much, but you provide electricity in an electrolytical cell. So you're actually recharging it, but when it's discharging, it's a chem cell again. We have this whole thing called the preferential discharge. So usually the electrolyte is the one that gets, redoxed, and say dilute salt water or dilute sodium chloride solution. When you electrolyze it, it's not going to release sodium on one side and chlorine on the other side. It's not going to do that. In fact, it's going to release hydrogen in the because hydrogen is positively charged. It's going to be released at the cathode, which is connected to the negative side, while the hydroxide ions are discharged at the anode, simply because A, the NaCl is not concentrated enough, B, the OH is preferentially discharged, and the H plus is preferentially discharged as well. But then again, you need to look at that table that I showed you guys earlier. So there's another table here, but it gets way crazier in the exams. You can also plate stuff, electroplating, copper plating, tin plating, yada yada. Just put the thing at the cathode and it gets plated. Easy peasy. Yeah, there we go, electrolysis. We made it. Yay. Now, let's eat some steak and also learn enthalpy. Now, what's up with enthalpy is that there are two kinds of reactions. The ones that release heat, they are exothermic, and the ones that don't release heat but absorb heat, they are endothermic. And exothermic reactions, in exothermic reactions, usually bonds are broken, but in endothermic reactions, bonds are broken. In exothermic reactions, bonds are formed. And we have a thing called enthalpy change. So if the enthalpy change is negative, then it's exothermic. If it's positive, it's endothermic. As you can see, there is a difference. Now we have the standard enthalpy change, which is basically enthalpy change, but in standard conditions, 25 degrees Celsius, 1 atmospheric pressure. And we have different kinds of enthalpy change of something, like standard enthalpy change of formation, standard enthalpy change of combustion, neutralization, and there are specific data because different reactions give off different amounts of energy per mole. So the unit is kJ per mole, and you can calculate it by a negative delta TMC, which we have learned in physics, over number of moles of the substance burnt if combustion, or the number of moles of water formed in neutralization reaction. And then we have the Hess's law, which can be very confusing, but if you get it, you get it. If you know, you know. So in Hess's law, so say you want to find the enthalpy change of this to this. So from this to this, what is the enthalpy change of this reaction? You can't find this, but you know what is this to this and this to this, which is connected. So you can actually just find this and this. So this plus this equals this. That is basically how I would explain it to you. If you go from point A to point B, no matter which path you take, it's all the friggin' same. That is basically Hess's law, and you see this little simple triangle in exams. You need to make another triangle, maybe more complicated triangles, a lot of complicated triangles. So complicated, I don't even see a triangle. Yeah, but hey, there we go. We have finished this book, the 3B. Now we move over to 4A, which is annoying because in this book we learn about rate of reaction. Rate of reaction, and we are at chapter 36. Hip hip hooray! End to my life. So at first it seems pretty easy. Rate of reaction is like, how fast is the reaction going. So you plot the concentration time graph of a product or a reactant, and you see how steep is the slope, and you find the slope by making a tangent line, like that. And there are different ways of checking the concentration, or maybe not. You can check other parameters as well: the pressure, the volume, the mass, the color change, if there is a color change, the acidity, even though that's, I don't know, complicated. But you can do all that stuff. And we're already over chapter 36. Over to chapter 37. We have a collision theory. So we need to explain stuff with the collision theory. Say ineffective collisions make a reaction happen, but an ineffective collision does not do that. So certain things increase the number of effective collisions, certain things do not. Like say if the reactants have a higher surface area, then the number of effective collisions are higher, of course. All right. So yeah, surface area, and there are other factors like catalyst. Catalyst speeds up the reaction. You don't necessarily get more yield. There are different kinds of processes that requires catalyst. The most famous one, Haber process, but we also got the contact process and other stuff. Worthwhile checking out. The Haber process is N2 plus 3H2 equals to 2NH3, 2 moles of ammonia. Pretty cool. Anyways, we are at chapter 38, which is the oddly easy chapter I'm talking about. Okay, I don't even need to flick the pages of this book to explain this. But basically, say you have 2 moles of whatever gas you have, carbon dioxide, oxygen, whatever, 2 moles. What is its volume? Well, 2 times 24. So this means 48 dm cube. That's it. That's all you need to know. That's all you need to know. Now, of course, there are so much more calculation in between, but we have already studied all those before, so you know what? Nobody cares. At the end of the day, we have dynamic equilibrium, because there are actually reversible reactions. There are reactions that are rather reversible, like when you're trying to ionize some ethanoic acid. I used to think it's dissociate, but I guess it's ionized because it becomes an ion. And as you can see, it depends because in a chemical equation, it's not always A plus B equals to C. Sometimes it's 2A plus 3B equals to 5C. Then the ratio it's going to be different for each different uh, um, reactant slash product used. But in a dynamic equilibrium, in a closed container, when this reaction, a reversible reaction, is going on, there must be a point when the reaction continues, but it has reached an equilibrium, meaning that the forward reaction rate and the backward reaction rate are the same. And you can actually find the equilibrium constant by this. The concentrations of the reactants divided by, not divided by, the concentrations of the products over the concentrations of the reactants. You find the reaction constant, which is actually constant, but you can actually change it by changing temperature or pressure, only these two things. There's also a unit of equilibrium constant, which is different in each kind of reaction. So you sort of need to use your mathematical brain to, deduce the unit. And then we have the QC. Kc is the equilibrium constant. The QC is the equilibrium quotient, which is not which is not about the equilibrium state of the reaction, more about that one instantaneous moment when I don't know, maybe in that one moment there are more reactants. The reactants are more concentrated than the products. So if the reactants are more concentrated than the products, then in that instant, the equilibrium position has shifted to left. And if it's shifted to left, the QC is larger than KC. Wait, it's not. I'm getting confused. The QC is larger than KC if the products are more concentrated because the products are on top. And when QC is larger than KC, then the equilibrium position shifts to left because there are more, the products are more concentrated. So you see, it's already confusing me. Again, there are several different factors. If you suddenly randomly add a bit of a reactant into this thing, it's going to behave like this. It's going to pop up and then slowly glide back down. But there are other factors affecting QC as well, like the temperature. If you increase the temperature of the reaction system, the setup, if the reaction is an exothermic reaction, it releases heat, then the concentration gradient of the heat is smaller, so the QC actually decreases. But if it's an endothermic reaction, the forward reaction rate actually increases because it favors the endothermic. Now we are on to our last book in chemistry, and that is book 4B. So, let's go. Actually, I forgot to talk about one thing before I talk about 4B. There's a specific way to calculate the equilibrium constant of a thing, of a reaction. So you need to make a table first of all, and in the table you have the reactants and the product, and in the beginning, of course, the product is 0 moles per dm cube. In concentration, of course. Okay, so here you go. This is very small, but you will understand. This is the table. So in the first row, it's the concentration, the initial concentration of the products and reactants. And then we have the change. And for the change, say 1 mole, 1A plus 2B equals to 1C. So if you don't know how many moles are gained during the formation of equilibrium, during the reaching of the equilibrium point, you can always just do, so it's 1, 2, 1. So, and A 1A plus 2B equals to 1C, hypothetically. So it becomes minus 1, minus 2, minus x, minus 2x, plus x. X is the number of moles. The number of moles lost / gained by the reactants / products are always the same. And then we have the equilibrium, which is essentially the initial concentration minus the number of moles. Yeah, again, I'm going to show you this thing. And if you understand it, you understand it. But this, the row 1, row 2, so row 1 minus row 2 equals to row 3, and then arrange it like this. And then you can find the Kc, and this is basically it. Alright, now we move over to the good old organic chemistry, the homolyzed theory series. We have visited this before, but we haven't visited this completely. So, first of all, in organic chemistry, only 4 types of atoms usually will appear. CHON, and O and N are not, they're not always, there, but C and H, they are essential. They are the essentials. So say CH4, because one carbon atom can form 4 bonds because it is at the 4th column with 4 electrons. So one carbon can form 4 covalent, bonds. CH4, and it's symmetrical, so it's nonpolar. CH4 is methane, and it is an alkane. If it's C double bond C, they can actually form double bonds. But because there's a double bond, the C can only form 3 bonds. Well, actually 4, but 2 of them are used in one other C, and then an H and an H. So I'm gonna show you what the heck is going on. Okay, so where is it? Okay. These are alkenes. They have this little equal sign thing, and it's actually the double bond. But if you check out the alkanes, you'll see that there aren't any double bonds. They're all pretty saturated. And then we have the OH. If a molecule ends with an OH or has multiple OH hydroxyl groups, they are now an alcohol. And there are 3 types of alcohols: the 1st degree alcohol, the 2nd degree, and 3rd degree, which I believe I've talked about already in the electives video. These elements are alcohols because they all end in OH. And if you have, like, I don't know, C whatever, C3H, H whatever, OH, then hey, it's an alcohol because it has an OH. And it doesn't have to be at the end, you can put 2 OHs, one at the end and one in the middle. Now it's a double alcohol. So, guess what? Next one in the series, we have carboxylic acids. So we have alkane, the normal one, alkene, C, double bond C, alcohol, OH. And we have carboxylic acids, which are acids, COOH. So all of these here, they all end with COOH, and they're all carboxylic acids. So they all share similar chemical properties, similar physical properties as well. Of course, the larger the molecule, the higher the melting point and boiling points, but you get the idea. Alright, now for something more special, haloalkanes. Haloalkanes are basically halogens plus alkanes. So we have CH4, of course, but you can actually swap the H out with, say, fluoride or a chloride or a bromide or an iodide. They're all fine because H offers one electron, and so does fluorine, and so does so does a fluorine atom, so does a chlorine atom, so does a bromine atom and an iodine atom. So FCl, Bri, haloalkanes basically. Haloalkenes are not possible. I mean, I'm sure you can make haloalkenes if you make it long enough. Then one part has the C double C bond and one part has the halogen thing, but generally it's kind of rare. All right, now we have aldehydes and ketones. Okay, so for aldehydes, we need a C double O bond. So as you can see here, C, and then it connects with an O with a double bond, and then beside the C, it's an H. So and that H is at the end, so no more beyond that H. Then that is an aldehyde. Then we have a ketone, which is similar, not to be confused, of course. Now, this my friend is an aldehyde because C double bond O and then H, and it's already the end. But this is a ketone because C double bond O and then there's another C connected beside. So, it's not the end, so it's a ketone. They are actually different. They're similar, but they're actually different. Up next, esters. Esters quite special because it's actually split into two parts. Now we have the chain of CH chain, and then C double O double bond O, and then connected to another O, which connects to another CH chain. So we have an O which splits in the middle, and when you try to name it, say in this one, because we have two C's, so it's ethyl. It starts with methyl, ethyl, propyl, butyl. Everything's like that: methane, ethane, propane, butane, pentane, hexane, heptane, octane, nonane, decane. So we have this thing YL, and then this thing O8. Yeah, basically there's that. So you get the methyl methanoate, ethyl methanoate, propyl butanoate. It's whatever. You can mix it however you want. The special thing about esters is that they smell. They give us a very specific smell. So pineapples, they release a specific ester to give a specific smell. Stuffs. Okay. Anyways, amines and amides. Amines and amides. First of all, we have an amide here, AMIDE, C double O bond, and then NH2. And then we have amines, which is just straight up without a double C double O bond, just an NH2. It can be here, it can be here, whatever. If it's just NH2 without the C double O, C double bond O, then it's just an amine. Now, you must be asking, there must be a connection between all of these, right? Yes, and I'm about to show you. Before that, here's the table, really handy table of all the kinds of molecules in the homologous series. The alkanes, alkenes, haloalkanes, alcohols, aldehydes, ketones, amines, amides, carboxylic acids, and esters. Now, the connection between them all. You can actually, okay, I'm going to skip a chapter. I'm going to return again later. The crazy thing is, I think I've had this pretty much memorized entirely already. But you can actually interchange between, say, you can actually convert an alcohol into an aldehyde, or an alcohol into a ketone, or an alcohol to an alkene, and then a haloalkane, and then to a carboxylic acid, and then to an ester, and then you can actually interchange them. But each one of these changes have different kinds of reactions. So I don't know where is the, oh, there we go. This is the almighty, the inner conversion table of each kinds of molecules and how they interchange with one another. I have a more simplified version of my notebook. and of course I will not talk about each reaction, but going from alkene to alkane, you need to break the C double C bond, a C double bond C. So you need heat, hydrogen, and platinum as a catalyst. And then alkene to alcohol, you actually need concentrated sulfuric acid, because the concentrated sulfuric acid has a dehydrating property. It takes an OH, alcohol to alkenes, concentrated sulfuric acid. But alkenes cannot directly change to alcohols. They jump to haloalkane and then to alcohols. Yeah, and then 1 degree alcohols. Again, alcohols that only have the OH connected to one chain of carbon. 1 degree, they can change to aldehyde by oxidation. So you can oxidize it with acidified potassium dichromate, turn it from orange to pale green, yada yada, boom, aldehyde. And then you can further oxidize it to become a carboxylic acid. And so to further do it, you actually can heat the thing under reflux, so it keeps on doing the reaction over and over and over again without stopping it. And then from carboxylic acid, you can actually make an ester by reacting a carboxylic acid with an alcohol, or and of course with concentrated sulfuric acid to snag away an H2O molecule, dehydration. And then you can also form an amide by reacting it with PCl3 and then an NH3. You can also reverse esterification and amidification by alkaline hydrolysis, which is basically react the ester with NaOH, or the amide with NaOH, and then give it some H2SO4 again, and heat, of course. Now 2 degree alcohols, you oxidize it, it becomes ketone. You cannot further oxidize it. 3 degree alcohols, OH connected to 3 chains of carbons, you cannot oxidize it at all. Basically, that's all you need to know. Okay, now isomers. There are a few kinds of isomers. We have the structural isomers. Isomers are basically similar molecules, okay? But actually, they're different. Say, there's a difference between pentane and 2-methylbutane. I mean, yeah, they have the same number of C's and same number of H's, but they're actually different. So we have a position isomer because the position is different. The chain isomer, which is kind of dumb because it means it's more, like 1 more carbon, I guess. We got the functional group isomer, which is also really dumb. And then we got the real ones, the hard ones, the stereoisomers. We have 2 kinds of stereoisomers, the cis-trans. So you can see the cis fats and the trans fats, and the enantiomers, or the optical isomers. So for cis-trans, cis-trans, I do this all the time, cis-trans. This only happens if there is a C double bond C. So this is a cis, and this is a trans. This is a cis, and this is a trans. You see the difference? Cis, both sides up or both sides down. Trans, diagonal. I almost dabbed. I swore an oath not to dab in my life ever. Yeah. So here's the thing. Trans isomers have a higher melting point because they pack tightly, because they're symmetrical. But cis isomers have a higher boiling point because they are asymmetrical, therefore polar, therefore harder to boil. Optical isomers, this is the most confusing one. Basically the mirror versions. So you can turn it into this format, this little tetrahedral format, and there's the mirror version of the molecule. Now they have the exact physical property, the exact chemical property. But the difference is that Optical isomers can rotate the plane of polarization of a beam of plane polarized light. Plane of polarization of a beam of plane polarized light. Remember that. Yeah, other than that, I have not much else to talk about. There are other kinds of very special hydrocarbons that you need to know, such as the almighty aspirin or acetyl salicylic acid. And its side effects, if you take too much aspirin, you puke. But it helps with, inflammation and headaches and stuff. We got soaps and soapless detergents. Not all detergents are soaps. We have, so for the soap detergents, we have the hydrocarbon tail and the ionic head, which is COO minus, and usually an Na plus. So this is a soap molecule. And one hydrophilic head. So the COO minus Na plus is the hydrophilic head. It loves water, and the tail hates water. So what it does is the head sticks to the watery part, while the tail sticks to the oily part, and they repulse against one another, so they rip it apart, therefore emulsifying the oil or the fat. We have two kinds of soapless detergent particles: the sodium alkyl benzene sulfonate and the sodium alkyl sulfate. All right, let's move on. Okay, so this is how you emulsify fat with soap. Let's move over to nylon. You basically react a dioic acid, basically carboxylic acid molecule, but both sides, and then a diamine, so two amines, both sides. You put them together and you turn them into polymers, basically repeat them over and over again. There are two types of polymers, right? There's the addition polymer, where before there's a double O bond, and then they do this. They do this, where the bonds break, and now they can all connect together, even though the double bond is broken, but they do this. If you see it, if you visualize it, it makes sense. And then we have the condensation, where you need a little bit of a concentrated sulfuric acid, and you snag away all the H2Os, so they all sort of condense, and that is basically what's happening when you're trying to form nylon. And then we also got the polyesters. Here's the thing, polyesters. This is a polyester if the ester functional group is not connected to the sides of the bracket, because this is a repeating unit. In a polymer, it repeats over and over and over again. There are long chains of this. If it's not at the sides, it's not considered polyester. So there is that. And we're good. Now for the final thing. Periodic variations are this easier. So, group 1 to 8, elements in periods 2 and 3, the metallic elements do their metal bonds, and the covalent ones do their giant covalent. Some of them do the simple molecular. The drill. This is the melting point, and these are the elements. The atomic number. See the melting points increase and then decrease again, and increase and decrease again. Silicon has a pretty high melting point because it has a giant covalent structure. And then we have the electroconductivity. Aluminum is very conductive because each aluminum atom has 3 electrons, so 3 delocalized electrons per atom. So the C is full of delocalized electrons, so it conducts electricity really well. And we got their oxides, their own oxides. So sodium oxide, magnesium oxides. These two oxides are basic. They're basic. So sodium oxide reacts with water. It becomes sodium hydroxide. So it's alkaline. Magnesium oxide reacts with water. It becomes magnesium oxide. So it's water. And if it reacts with an acid, it neutralizes it and turns it into salt. Amphoteric is aluminum oxide because it reacts with both acid and alkali to turn it into salt, which doesn't have any pH. It's neutral. Silicon dioxide is kinda alcohol, kinda acidic, technically. And phosphorus pentoxide, of course, acidic because it can become phosphoric acid. Sulfur can become sulfurous acid or sulfuric acid, and of course, the chlorine oxides are all really acidic. And that's pretty much it. We have finished the entire chemistry syllabus. It's about to be 1:30 a.m. I want to go to bed. Goodbye. Oh yeah, transitional metals like iron or manganese or cobalt or nickel or zinc. Um, they can have multiple oxidation states. B, they can actually express colors. So iron 2, it's green. Everybody knows that. Iron 3 ion, though, yellowish brown. Permanganate is purple. Manganate, colorless. Dichromate, it's orange. Chromate, it's pale green. And another thing is that you can use them as catalysts. The rhodium, platinum, iron, finely divided iron is a catalyst for Haber process. Vanadium oxide, V2O5, is the catalyst for contact process, and which is a process that produces sulfuric acid, I think, because it's such a strong oxidizing agent. You need to make a process for it. So there's that. Another thing I forgot to mention is the Markovnikov's rule. So say bromine solution dissolved in an organic solvent like a tetra, like whatever, like a pentane. So Br2 added to a chain of CNHs, a chain of CH, a hydrocarbon, an alkane, or an alkene. Which side is it going to stick to? For Br2, it's going to stick to both sides of the double bond. But if it's HBr, then the H is going to stick to the shorter side, because that side has less H, but the Br is going to stick to the longer side. So that's the Markovnikov rule. And this is the major product where the H sticks to the short side, Br sticks to the long side. But sometimes it's not like that, and that's usually the minor product. So there's that. I mean, there may be a lot of other stuff that I forgot to talk about, but yeah. Oh, I forgot to talk about cracking. Cracking is where you crack a gigantic alkene, and you crack it in half or into different pieces into a smaller alkene or smaller alkanes, and you can do that by soaking the big alkene into a cotton wool. You put it at the very end of a test tube. You place the test tube horizontally. You put some broken unglazed porcelain because they act as the catalyst. You heat it up and you can sort of crack it. It's my favorite reaction. It's endothermic as well, so that's pretty interesting. Combustion is exothermic, however. Another thing I forgot to mention is the catalytic converters, which you can install in your cars in order to save the environment. Basically, carbon monoxide and I think nitrogen dioxide reacts to become carbon dioxide and nitrogen, which are way harmless than carbon monoxide and nitrogen dioxide, because nitrogen dioxide and sulfur dioxide can also react with rain to become acid rain. And also you can install scrubbers in your industrial machines to remove sulfur dioxide. And yeah, that's basically it.